So as I mentioned, so it's just practice. So I will not count your attendance for 2 weeks, right? So, but we need to be familiar with the new system, new attendance check system. And then, so as I mentioned in the first class, so I will not check your attendance manually, right? So you need to check, right? And then also, so this is the strict rule. So if you miss so 1/3 of the entire classes, then you will get F in this course. So this is just it's like a law from government. Okay, it's a rule. It's a strict rule. So you need to check. And then also after this semester, so I need to submit the proof of your attendance to the department, right? So it's critical, right? So you need to check your attendance using this self-attendance check system. So sometimes in the previous semester, some student asked about so they did not check their attendance during the class, and then they asked about some solution. But so so this is just the system, and then the history is automatically stored in the system, right? So please, so do not forget about this self attendance check. Okay. Okay. So how you? Okay. Okay, let's get started. So in the previous class, so I explained why we need to learn computer architecture in the computer engineering department. So it is required for understanding the computer system. And then, as I mentioned, the computer system is composed of software part and hardware part, right? And then in the computer architecture course, so we will focus on the hardware part of the computer system and the software hardware interface. So we will learn about some abstraction levels and then some layers in the computer systems, and then you can find that the computer architecture layer is located in the lower layer, the lower layer of the computer system, right? So it's because it's hardware. So and then everyone knows that the software runs on the hardware system, hardware part of the computer system. So we can say that the computer architecture or computer hardware is the lower layer of the computer system. Okay, and then so now in this time, so we will discuss about the abstraction, the concept of abstraction in a computer system. So I briefly explain about the abstraction, the meaning of the abstraction. So you can in Korean, so because it's in Korean the abstraction is just 초록 in paper. But what is abstraction? What is the meaning of abstraction in our normal life? It's a normal world. So you can find abstraction part in academic paper or in a textbook. So you may find the abstraction section or preface, right? So what does that mean? So in a paper, academic paper, abstraction is just the summary of the paper. So what does that mean? What is the abstraction in a computer system? The summary of a computer system, right? But in order to summarize the target content or target system, we need to simplify, right? So detail of the system or detail of a paper or detail of a book can be very complex or complicated, right? But in order to summarize the target system, we can simplify. We can simplify the target system, or we can simplify some target paper. So this is the, so you can understand the abstraction like this. So this slide shows the analogy of abstraction in our real life. So what can you see? So you can find a cute girl, and then this cute girl is driving, right? So and then but it's not available, right? But so let's think about the car driving. So actually a car is a very complex system, right? So car is composed of engine systems, and then control systems, and then brake systems, and so on. But and then actually this car is very complex. But in order to drive a car, which knowledge is required? So do we need to understand the entire systems or entire control systems and the entire mechanical systems of car? No, right? No. So we don't need to understand the entire systems in a car because it's very complex. So in order to drive a car, we just need to understand how to use a handle and some pedals like acceleration pedals and brake pedal, and then some other systems such as some other control system like control buttons, right? And just that. So you can find that this is the abstraction layer. So actually under the car, inside of a car, as I mentioned, a car includes very complex systems like that is engines are very complex, right? And then brake system. So those systems are very complex. But we don't need to understand the detailed mechanism or detailed theory in the car, right? We can just understand this abstraction layer. So what does that mean? Abstraction means we can simplify a certain system to in order to use a certain level of a system, right? So you can just understand that the abstraction is kind of a simplification, okay? But in abstraction, the required knowledge, such as the handle and then some pedals. So those are required knowledge for driving a car, right? But this required knowledge is revealed to users or operator. Okay, only the required knowledge, is revealed, but the complex part, and then we don't need to use this complex part. Then this complex part is simplified. So this is the concept of abstraction in a system. 아침 수업이라 좀 쉽지 않아요. Sorry about that. So this is the concept of abstraction, and then actually, so we will learn about a computer system, right? And then, as I mentioned, a computer system is a very complex system. So how can you learn? How can you learn about this complex system? We will just focus on a certain layer of in a computer system, and then other layers will be simplified. Okay, let's see this slide. So this is the meaning of abstraction. The meaning of abstraction is hiding details when they aren't important, right? So it's a simplification. So aren't important. So which means that it is not required for using. Why it is not required for use, or it is not required for understanding for a certain layer. So this complex part is just simplified or ignored. But by the concept of abstraction, required interface or required information is revealed. So we need to understand this required information, required interface. Okay, so this figure shows some layers, so abstraction layers in a computer system. Okay, so So you can find that there are many layers. So there are many layers in a computer system, and in this course is the computer architecture course. So we will focus on the microarchitecture layer and architecture layer in a computer system. So our course, so COSE 222, the 222, will cover these layers, so architecture layers and microarchitecture. So if you see some content in this layer, the microarchitecture includes the data path. So we will learn about the data path and then control part. And then architecture include instructions and registers. Okay. So in this course, we will focus on these layers. Then how about the underneath layer? Actually, if you took the digital logic design course, is a COSA 221, then this course covers the logic layer and digital circuit layer. So we learned about some components, the digital computation components such as adders or memories, right? So, and then we also learned about some gate level circuits in a digital logic design course. So this is the very detailed the logic design. Okay, so the digital logic design course includes these layers, logic layers, and then digital circuit layers. But actually, so we are learning this layer, microarchitecture or architecture layers. Then how about these layers? We can just simplify. We can ignore some detailed behavior of logic or digital circuits in this course, because this part is very complex. And then in order to understand this layer, microarchitecture or architecture, so we don't need to understand the detailed behavior of these components like logic or digital circuits. So it is simplified, and we just focus on these layer. And then after this course, you may take the operating system, right? Operating system is a software, right? Then if you learn about the operating system, the hardware part, like architecture, can be simplified. You can just focus on this operating system layer, and then underneath knowledge can be ignored. Okay, so this is the concept of abstraction. So we can just focus on a certain layer in a computer system. Then other information can be simplified or ignored. But in order to learn, in order to build the entire computer system, all layers are required, right? So for example, so if we are learning about the operating system, then actually you can find that operating system requires the these underneath layers, all layers, right? Then actually this architecture layer interfaces with this operating system layer. Then what is required? In order to design or in order to learn about the operating system, then you need to also understand these interface signals. Okay, because these information or data or signals will be delivered from the underneath layer, like architecture layer. Okay, so actually we can focus on a certain layer, but we also need to understand the interface signals. So this is the concept of abstraction. So then, what is the benefit of abstraction? The benefit is we can understand the very complex system with a easier manner, easier manner, right? I said easier, okay? Because we cannot, it's very difficult. It's very difficult to the entire layer knowledge, complex system, right? We can just focus on a certain layer in a computer system, and then so we can easily understand. It's not easy, that easier, right? But what's the problem? Also, we can find the disadvantage of this concept, abstraction concept. Optimization. What does it mean? So if we just focus on a certain layer, for example, operating system, then we just assume that the underneath layers are perfect. Okay? So, and then we just understand some interface signals, some data or interface signals from underneath layer, like architecture layer. We just focus on the operating system, like a software part. The problem is that, so we just assume the underneath layer is perfect, but it's not true, right? So actually, we just focus on optimizing only this part. So co-optimization. So sometimes we may think about some software or hardware co-optimization, because so if we just apply the co-optimization to the multiple layers, then we can just apply some more efficient optimization techniques. But if we just focus on only a certain layer, one layer, it's not possible. So disadvantage is optimization. Okay. But we can understand these computer systems like this. So this is the easier way. Okay. And then in this course, as I mentioned, so we'll focus on the architecture layer, like instruction set architecture, and microarchitecture, the processor architecture. Okay. Okay, let's see the example. So this slide shows the die photo of a CPU. So what can you get from this image? So you can find, this. So actually, these are digital circuits, right? Actually, the digital circuits are composed of CMOS transistors, right? But in this figure, this is the die photo. Actually, you can find many transistors here, but transistors are very, very small. So you cannot count. Okay, so actually, this is just a die photo. And then you can think that, this is just beautiful, and that's it. We cannot get any information from this figure. Then we can change some abstraction level. So in this figure, I just draw some rectangles, and then I just write the name of components. Okay, so this is the Intel i7 chip diphoral, and then you can find that, oh, this part is the memory controller part, and then you can find 4 CPU cores, and then this is the GPU part, and then, oh, this is the L3 cache, and then L3 cache is distributed to the multiple cores, blah, 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 blah. So abstraction level is different. So actually, in this part, you can just see transistors, right? But it's very small. But we cannot get any information from this part, this photo. But if we just make some add some figures like rectangle figures, and then if we just classify the components, then we can understand. You can understand this understand about the Intel i7 CPU. i7 CPU includes 4 cores and embedded GPU, and then interconnection network, and then shared L3 cache, something like that. So this is the different representation of this CPU, but we can understand. We can get some information from this different representation. Okay. So inside the processor, then the processor includes this part. Then we will learn about this part. Okay. So, but in this photo, we can just find that, oh, this is a CPU, and that's it. Then how we don't know how this CPU is organized. So this is some different abstraction level. Actually, Intel CPU, Intel core can be described like this. So you can find that, oh, this is so small, right? So you can actually, you don't need to understand about this architecture, because this architecture is actually this architecture just to implement some advanced architecture, advanced process architecture. But in this course, so we will learn about the very simplified and basic architecture of CPU. But modern CPU includes the different architecture like this. Okay, but it's just an example. So I just show some example of abstraction, the example of the processor architecture. It's a microarchitecture level abstraction. So microarchitecture represents the architecture of core. It means you can find the CPU core here, okay? And then microarchitecture represents the architecture or structure of this CPU, right? So you can, and then we can just describe the CPU architecture like this. You can find the many components, okay? And then you can also find those interface signals between components. So as I mentioned, you don't need to understand this figure, okay? So for example, so this is the branch prediction unit. Okay, and then the branch predictor is interfaces with the L1 cache, instruction cache, and then the stream buffer. So we can just understand some detailed structure or detailed architecture of the CPU with the different abstraction level. Okay, but we don't know how the branch predictor is implemented. we can implement branch predictor using logic gate or some digit, digital component. That's what we learned in the digital logic design course, right? But in this figure, we do not represent the detailed implementation of this branch predictor, okay? Because this is the microarchitecture level abstraction. We just shows some components and then how these components are connected with other components in a microarchitecture. Okay, so do you understand? So this is a different abstraction level. Okay. Okay. So this is the so this is the concept of abstraction, right? And then okay, so below your program. So actually, when we use a computer system, so we interface with software, right? So actually, we just use software running on a computer system. So that's why most people think that software is just a computer, right? So we frequently say that oh, I'm using computer. I am using a computer. So which means that actually it means I am using on software or application, right? So, but everyone knows that the a computer system is composed of the software part and then hardware part. So we can understand it like this. But we just use this application software, right? And then under this application software, there is system software, okay? Actually, the system software manages the execution of our application. The system software includes some driver, operating system, or some protocols, okay? And then also system software includes the compiler, okay? So, and then underneath of this system software, there is hardware, okay? And system software manages the hardware part of a computer system. So you can understand a computer system like this. So application layer, and then system software layer, and then hardware layer. So this is the simple representation of a computer system. So then let's see how our program is translated. So what does that mean? Actually, so as I mentioned, we use an application. Okay, it's a software. How can we make or how can we build an application? We can write a code. Okay, we can write a C code, or we can write a Python code, which means it's called coding, right? Then we can make a some we can make a code. Then how can we execute this code? So when we write a code, we can we can understand because the code syntax is similar to English language, right? So we can easily understand our code. We can just if we just understand the syntaxes of a programming language, then we can understand the code, right? Then how about the computer? Well, how about us hardware? So, if you took the logic design course, then you can, I believe you can understand that the hardware is a digital system, right? So what does that mean? What is a digital system? A digital system can process or understand only digital signals. So what are digital signals? So digital signals are composed of zeros and ones. And then actually zero is zero and one is one, but zero represent the low voltage. Okay, so electric signals, right? And then one represent the high voltage, right? But anyway, we can represent 0 and 1 using voltage levels, high voltage or low voltage. That's it. And then digital system. A digital system can only understand digital signals, 0 and 1. So what does that mean? Our code is similar to our natural languages, English, right? Hardware, hardware can only understand the digital signals. It's different. Digital signals are just zeros and ones. So what is required? Translation. So languages are different. So it's a high-level language. This is the programming languages. And then hardware just to understand the digital signals, 0 and 1. So high-level language code needs to be translated into digital signals. Now, these digital signals are called a machine code, a machine language. Okay. So actually, if we write a code and then in order to execute our code, some translation is required. This translation is called compilation. So, and then it's done by compiler. So in Korean, we frequently say a compiler, compile. But so, but we require compilation. Okay. So this is translation. Then this process is the compiling process. Okay. And then we require compiler. So firstly, our high-level language code is compiled, and then actually the assembly language program is generated. It's also kind of a translation. Then what is an assembly language code? So this is the example. So it is a high level language code. So you can find the swap function here written in C. You can, I believe, if you are familiar with the C code, and I believe you can easily understand the meaning of this code, right? This you can. So these are English letters, right? So you can understand. But after compilation, then assembly language code is generated. So you can also find the English letters, but it's different, right? You can find the, oh, what is this? Add, load, some instructions, and then what is the X6, X11, 3, right? So actually, this assembly code includes the instruction. Okay, so we will learn about the instruction later, right? And then, so this is the instruction, and then this instruction is executed by a CPU or processor, one by one. Okay. So when we see this code, so we already understand that this code is executed from top to bottom. Assembly code is the same. Actually, this code is executed from top to bottom. The firstly, SLLI is executed, and then add is executed, and then LD is executed, blah, 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 like this. But what does that mean? So I mentioned that, oh, firstly, SLLI is executed, then add is executed, then LD is executed sequentially. But what does that mean? So you can find that one line, this one line of assembly code is executed. And then next line is executed one by one. Okay. So this is called, so these are instructions. And then one line of assembly code represent a single instruction. And CPU execute instructions one by one from top to bottom for this sequence. Okay? But question is that, oh, we can just find, oh, instructions are, uh, instructions include English letters, high level language actually. So CPU is a digital system, kind of a digital system. A CPU cannot understand this. So using assembler, these instructions are translated into the machine code. Okay, you can find many zeros or many ones here. But this translation is just one by one mapping. So what does it mean? This instruction is translated into this one line of machine code. And then the next instruction, add instruction, is also translated into the next line of machine code. Something like this. So it's a one by one mapping. Okay. So it's very simple. Actually, the compilation from high level language to assembly code is a little bit complex. That's why, so you will learn about this compilation process in the compiler course, not this course. But this assembly to machine code is just a one by one mapping. It's just encoding. Okay. So based on the simple encoding rule, we can just translate this assembly instruction into a machine instruction. Okay. And the machine instruction includes just 0 and 1. So these are some processes for executing our programming code. Okay. So actually, in Nautic, we can just write a high-level language code using C or C++ or Go, Swift, some other languages such as Java. And then, but we can easily understand this high-level language code, but in order to run this code, then our high-level language code need to be translated. And then this translation includes the compilation. So compilation, just compiler, just translate our high-level language code into the assembly code. And then assembler translate our assembly code into the machine code. Okay. Then CPU reads this data. It's because this is the digital data, right? Then CPU execute this machine code. That's how a hardware works in a computer system. Okay. Okay. So so you need to understand this actually, because that's it's a real world. So actually, so we are uh so normal person, normal people just interface with the software, but the software is just kind of the virtual world. It's a fantasy world actually. Actually, the hardware is the real world component. Then actually in a real world, hardware just execute this machine code. Okay. Okay. And then, so I briefly, so this is how our program is executed in a computer system. Okay, so let's see some common components of a computer system. So in the first class of this course, I just showed some typical computer machines, right? So if we just think about a computer, then we can think that a computer is composed of display, well, monitor, and then input and output devices such as keyboard or a mouse, okay? And then also the computer includes the large box, okay? So, and then actually if you, so and recently we frequently use a laptop. So it's not easy to open the lid of the laptop. But if you use a desktop, then you can just open the desktop box. Then you can find the large board and then some chips. Okay. And so actually, our computer system is composed of many components. As I mentioned, the I/O devices such as a keyboard and mice. Also, our computer system is connected via network, right? So it means our computer includes a network interface. Also, our computer includes the display and CPU and memory. Okay, so this is the the photo of the main board of a computer system. So as I mentioned, it's not easy. So recently, it's not easy to open the lid of our computer, right? It's just it's a very small, and if we leave some this device, then it can be broken. So it's not easy. But anyway, but actually, our computer system just includes some many components, and then our computer system is implemented using this large board. So this board is called a main board or motherboard. Okay. So actually, a computer includes the many components on board. Okay, you can find, so in this figure, you can find this part. This part is the CPU, and then the CPU is connected to the memory. Okay, main memory. So it's the same to our mobile phone. Our mobile phone includes application processor, but actually this is a CPU. And then, if you read the specification of your smartphone, you can find, the size of memory is like 6 GB or 8 GB. So this is the actually main memory. It represents the size of the main memory, this part. And our computer system is connected to many input and output devices. It's the same to our smartphone. So we can touch this display of the smartphone. So this is the input interface. Also, our smartphone can be connected to the camera. So this is also kind of other input devices. It's the same. Actually, our computer CPU is connected to the other components. You can find those other components here. Okay. And then these components are also connected via the network, interconnection network chip in the computer system. So it's complex, right? So in the abstract, with some abstraction level, we can represent a computer system like this. But you can find that this is the computer system architecture, but old, right? It's an old computer system. So as I mentioned, this is a CPU, and then CPU is connected to the external memory. Okay. I mentioned this is the external memory because this memory is out of CPU. So actually the CPU also includes the internal memories. Okay, like this memory is called the cache. Okay. So using the memory bus, then CPU is connected to the memory. So these are different chips. the different chip. And then using a system bus, then CPU is connected to other components like graphic card and then I/O devices. Okay, but you can find that this is the old computer system. The modern computer system looks like this. So recently, the GPU is very important in our system, right? So what does that mean? Important. Import, important in our computer system. What does it mean? A large amount of data needs to be processed by this component. Okay, and which means we require high bandwidth. Bandwidth is the amount of data transferred in a unit time, within a unit time. And then I mentioned that a large amount of data is processed by GPU. So, which means a large amount of data needs to be transferred between CPU and GPU. Then what is required? So this is the real world, and then a large amount of data transfer is required. So which means we require high bandwidth channel, data channels. So data can be transferred via data channels only. Okay, so this is hardware, and this is real world, right? So it's similar to a road. Okay, so if if there is only a small number of cars, then we can use the narrow road, right? But if there are many cars, then we need to build a wide road, right? It's a real world. And then hardware is a real world, right? So if we require high bandwidth data transfer, then we require high bandwidth data channel. Okay? It's like road. Okay. So in a modern computer system, the CPU is directly connected to GPU via high bandwidth channel. Now you can find the memory here. So also the CPU also demands a large amount of data from our external memory. So this memory channel is also the high bandwidth channel. Okay. And then the CPU is connected to the I/O chip. I/O chip of a computer system. This is the mainboard chip. And then via this I/O chip, the many other components are connected. Then why? Why the GPU is directly connected to the CPU and the memory is directly connected to the CPU, but these devices like the storages and a keyboard and mouse and network is connected via I/O chip. What's the reason? Why? Why do we organize a computer system like this? So I mentioned a road, right? A road, the traffic system. If there are many cars, we need to build wider road. So it's the high performance traffic system. But if there are a small number of cars, then we can build narrower road. So it's a low performance traffic system. It's the same. It's the same to the computer system. So high bandwidth data transfer is required. So in this case, then we build a high bandwidth channel between CPU and other components, and then CPU directly control these channels because we require high bandwidth data transfer. But these components, network is slow, keyboard is slow, mouse is slow, storage devices are slower than memory. So it means we require low performance, low bandwidth. So our system is designed hierarchically. And then this is some main approach, some primary approach for building a system actually, right? So if we require high performance, then GPU can directly manage the data transfers between this component. But if not, if the IO the performance is low, and then also if we don't need the high performance, then it is managed by some IO chip, the different, so lower level controller. Okay, so this is some typical design policy of a system. Okay, and then we can build a system hierarchically like this. Okay, and then this is some typical also some. So I just copied this figure from the Intel mainboard chipset specification. So you can, if you read this specification, then you can understand, oh, this chipset is actually the computer system. A computer system is organized like this. Okay. So why did I explain this? It's also another abstraction. Okay. We can just find some components, actually rectangles, right? And then we can just find some connections like line, and then a CPU, and some other parts. But using this figure, we can get some information, right? We can understand how a computer system is organized. Detail is hidden. A detail part is hidden, right? So we don't know how this component is implemented, and then we don't know about some logic design, what is the circuits inside of this part. But we just simplify this component, and then we just show how a computer is organized. So it is also some different abstraction level. Okay. So actually in this course, so I will explain computer hardware like this. Okay. So detail like digital circuit or some other logic design is just ignored. And then I will just show some components like this, right? It's just a rectangle. Then I will explain how computer is, or how a processor is organized. Okay, so then I will briefly explain about some technology underneath the computer system. Okay, actually a CPU. Okay, so we are learning about computer hardware, right? And then everyone knows that in order to build a CPU chip, we require semiconductor technology. And then recently, this semiconductor technology is very critical, right? So if you read news, then you can find, oh, the TSMC developed a 2 nanometer or 3 nanometer technology, but Samsung is struggling. So what can we do? Something like that. And then also the Intel is just developed the 10 nanometer technology. So, but the quality is so low, so Intel is also struggling, and then stock goes down, so Intel is uh, also lost profit, something like that. So actually, semiconductor technology is actually very critical, critical for the industry of nations, right? Why? Actually, a CPU is a chip, okay? And so which means the CPU performance is determined by semiconductor technology, right? Because uh, you can find layers here, okay? So you can find but these part digital circuits and the analog circuits and then devices. So actually the semiconductor technology covers this part, right? It's a very fundamental layer. So actually the performance of this part, the lower part, the fundamental layer, decides the performance of upper part, right? So semiconductor technology is here. And then actually, so which means the upper layers are uh, dependent on the lower layers. Okay, so we can just design upper layer based on the current levels of lower layer. That's why the semiconductor technology is so critical. So, for example, architecture. Architecture is also developed, and then the advances in the architecture is highly influenced by semiconductor technology, right? So that's why the semiconductor technology is so important. Okay, so this figure shows the graph, the DRAM capacity graph, and then x-axis represent the year, the time, and then y-axis is the capacity of a DRAM chip. And then you can find that this y-axis is the log scale, okay? And then the size of the capacity of a DRAM chip increases linearly in this graph, right? But you can find that y-axis is the log scale axis. What does that mean? The capacity increases exponentially. So actually, like this, like so, it looks like to the time, right? Exponentially, right? Because this y-axis is the log scale. So and then, so what does that mean? DRAM capacity is increased. Then why? How? So everyone wants to use large memory. So think like this. If you purchase a smartphone, oh, this smartphone includes the 2 GB of memory. This smartphone includes the 8 GB of memory, and then price is the same. So you will buy 8 GB of smartphone, right? Memory size is very critical. So everyone wants to use large memory. Oh, memory capacity is increased exponentially. That's a good thing. Then how? How how can we increase the capacity of memory? So what is the memory? So the memory stores the data, right? Store. So actually, memory requires storage space, right? And then in this storage space, we can store a digital data, 1 and 0. So in the same area, in order to store more data, then this size of a single storage space needs to be small. Obviously, right? What does that mean? Actually, the memory looks like this. This is the transistor, and this is capacitor. And then transistor and capacitor can be implemented using semiconductor, right? So in order to increase the capacity of memory, we need to reduce the size of transistor and size of capacitor. What does that mean? We need to develop semiconductor technology that can implement smaller transistor. So, TSMC is developing 5 nanometer technology, and then 3 nanometer technology, and then 2 nanometer technology, like this. So you can observe this number is reduced. And then this number actually represents the size of a transistor. So when semiconductor technology advances, then we can build smaller transistors. And if we can build smaller transistors, memory capacity can be increased because the size of the storage space is reduced. Then, which means in the same area, we can store more data. So I believe you can understand why the semiconductor technology is critical, right? So we need to build, we need to make smaller transistor, okay? So if a semiconductor technology is improved, then we can increase the capacity and also performance of CPU and memory. So which means we can use faster CPU. And then the cost, even the cost is reduced. Oh, that's very good, right? The performance is increased and then cost is reduced automatically. Oh, it's very good, right? So that's why the semiconductor technology is critical. Okay. So this is the, actually we can build actually the semiconductor technology. So we can use a silicon because the silicon is a semiconductor, right? 반도체. So conductor is a 도체. So we can, it's something like a metal, and then the dielectric, insulator. The insulator is different, but semiconductor is between the conductor and insulator. Okay. So this is the relative performance per cost. So 1951, we can use the vacuum tube. So it's one, and then currently we can use the VLSI or ULSI, the ultra large scale IC. You can find the relative performance per cost. So what does that mean? Cost is reduced, performance is increased. Then we can use very good CPU with low cost. It's very good things, right? So this is the semiconductor manufacturing process, okay? And then, but when we build a processor or when we build a chip, then we can also require the manufacturing cost, right? And then this manufacturing cost is determined by size of a die, a chip. So this is because when we make a wafer, this wafer can include defects due to some other materials. Then we can find defective chips. And then if the chip includes defects, then we need to remove this die. We cannot use. So, and then this probability is proportional to the area, the area of a die. So actually, so which means actually the cost is related to highly dependent on the size of a chip. Okay. Okay, so this figure shows the 300 millimeter wafer. So wafer looks like a circle and then a chip or die. So this is the one single die. Okay, so you can find many chips or many dies. Okay, so this wafer includes the 280 chips using, and then this wafer is manufactured using 32 nanometer technology. And then each chip size is like this. Okay. So this is the same size wafer. But you can find that, oh, there are more chips. Why? The size is reduced. How? 10 nanometer technology. What does it mean? The transistor size is reduced. So I mentioned that this number represents the size of a transistor, the 32 nanometer technology, and then 10 nanometer technology. So as you can see, this is the Intel i7 wafer. But the wafer size is the same, the 300 millimeter wafer. But this in a single wafer, we can include many chips, and then chip size, because chip size is reduced. So which means we can make more chips from a single wafer. Also, the cost is reduced. Why? Transistor size is reduced. Okay. So actually, this cost is also determined by yield. So this is just some equation, but you don't need to memorize this equation. But you can just understand that the cost of a chip is determined by the size of a chip, what die. Okay. Okay. So in order to build a better chip or better CPU, then we require more advanced semiconductor technology. What's the problem? Samsung is struggling, Intel is struggling, TSMC is, is TSMC is doing well, but cost is increasing. Why? I mentioned this number is represent the size of a transistor. So, and then it's not easy. So making a smaller transistor is so difficult recently because size 2 nanometer, it's very small, right? It's just very similar to the size of element, really punja size. So there is a limitation. There is so making a smaller transistor is getting more difficult. The cost is increasing. So that's why Samsung and Intel is struggling now, right? So then, which means the technology is changing, okay? But uh, but in this course, so we just assume that we will learn about the very basic knowledge on CPU design. So we do not consider about the recent trend of in semiconductor technology. Okay. Okay. So then the next topic is performance. But so I need to stop here. I will stop here, And then in the next class, we will learn about the performance metric of a computer system. Any questions? Okay. Thank you for your attention and then see you in the next class. 감사합니다.